Okay, so in the last lesson, we thought about the sample mean as a random variable because it's a function of the random sample. And because it was a random variable, we could find its expected value from the expected value of the x sub i's. And in finding that, we saw that it was an unbiased estimator of the population mean. So that was a lot to do. We're going to continue in this lesson to think about the sample mean. So that's m sub n. Just add up the x's and divide by n. We're going to think of it as a random variable. And in this lesson, we're going to study its variance. Okay, so let's see what we can figure out about the variance of the sample mean here. And to kind of get us warmed up, let's just remind ourselves of some things we know about variances and variances of functions. Okay, so some things that we learned earlier in the quarter. One thing we learned is that the variance of a constant times x is the constant squared times the variance of x. We derived that at some point during the quarter. And we also found that the variance of x plus y was the variance of x plus the variance of y plus 2 times the covariance of x and y. Okay, that's fine. Another thing that we didn't make too much of at the time, but it's going to matter for us right now, is this implies that the variance of a sum is the sum of the variances when x and y are independent. Okay, and because the x sub i's in our random sample are assumed to be independent, this red point here is what's going to be relevant for us. So the variance of a sum is going to be kind of the easier thing to calculate when we don't have covariances to worry about. All right. So we've got those little notes from useful things that we learned in 200A, and let's bear those in mind as we look at what it means to look at the variance of the sample mean. So we're taking the variance of x1 plus x2 all the way up to xn. So we're just adding up all the numbers in our data sets, all of our observations on x, and dividing by n. Okay. And let's just maybe split that up into the sum of the variances. Okay, remember we said these are all independent because it's a random sample. Random sample means that the x's are IID, that stands for independent and identically distributed. So the variance of this plus this plus this is the variance of this plus the variance of that plus all of the individual variances here. So using that, we have this equals the variance of x1 over n plus variance of x2 over n. Do this to all the x's in our sample till we get to the very last one. Give myself a little more space to write here. X sub n, that's our last observation. Okay, so it's the variance of the sum is the sum of the variances because our x sub i's are assumed to be independent. Great. Now we're going to apply this rule. We're going to pull out the constant 1 over n. So in each of these cases, it's 1 over n squared times the variance of x1 plus 1 over n squared times x, the variance of x2, again, all the way to the end of the sample. We'll do that to every term. Okay, so 2 things to do. One, I'm going to factor out all these n squared terms. So that's the same for all of them. So it's 1 over n squared. And then I'm going to remind myself what the what we know, or how we talk about the variance of x1, the variance of x2, the variance of xn. We don't know what the number is, but we know these variances are all the same. We know it's all the same because that's what it means to be identically distributed. Okay, so if this one has variance sigma squared, that one has the same variance sigma squared, they all have the same variance sigma squared. So each of these terms is sigma squared. And just as we did with the derivation of the mean, so we've got sigma squared here for all n of the x's. That means that there are n total factors there, n sigma squared divided by n squared. This is what we get for the variance of the sample mean. Okay. So it's not exactly sigma squared, but that's fine. We're not trying to estimate sigma squared here. We're trying to find something about the variance of a statistic that we use to estimate mu. Okay, and what we find out about the variance is kind of two things about it. So first of all, the more variance there is in the process that generates the x, the more variance there's going to be in the sample mean. Okay, that makes sense there. But there's going to be less variance in the sample mean the bigger our sample is. And this is the really important thing. Okay, you might have been wondering in the last video when we're saying, well, we can use the sample mean to estimate the population mean. And we can do that because its expected value is mu. Well, the expected value of x sub 1 by itself is also mu. And if we just had x sub 1, if we just had one observation, if we were journalists and instead of collecting data, we just talked to one person, that would be our best estimate of the sample mean, the value for the one observation that we have. But what this is telling us, this information about the variance of the sample mean, is that it gets smaller the more data we have. And that is a good thing for an estimator. That's the other really good property that we want our estimators to have. We want them to have low variance, and in this case, variance that gets lower as the amount of data gets larger. So low variance in the sample mean means that as n gets bigger and bigger, what we get for the sample mean, what we get for that number we can actually calculate, is going to be closer and closer to the true value, the population mean, mu, the thing that we don't know. Okay. So that's a really cool thing. And this fact is, the mathematical justification for an idea that most of us already have, that more data is better. If we have more observations relevant to the same thing, that we're going to get a better estimate of it. And this is kind of a mathematical proof of exactly that.